Here we have an Arduino Nano with the capability to display the states of switches into a bar graph as binary values. Here's the parts table. So first, let's shift some binary values into the bar graph. Let's represent the decimal value 106, let's say on the bar graph. That would be 01101010 in binary. So let's do that value. Now let's represent another value. Let's say 246. So that would be 11110110. So first we actually have the chip itself, the 595, and the main parts of it are really the data, latch, and clock pins. So the clock pin controls the timing of the shift register, determining when each bit is shifted in. The SER pin is the serial input for the shift register, and it's where you provide the data bit by bit. The latch controls when the data is latched into the output register, updating the output pins, and it also has 8 outputs which are connected to the bar graph. Now let's see the code. Alright, so there are 3 things that need to be defined for the 595 chip, which are latch, clock, and data. Next, in the setup, we need to make sure that latch, clock, and data are outputs because that is what we are using them for. The Nano is constantly checking the state of the switches, so which are outputting highs or lows to these pins, so that the 595 can imitate the state of the switches onto the bar graph. So here we have all the switch pins, which is why it's called S, which are pins 5 through 12, and the line inside the for loop sets the pin mode of the switch pins 5 to 12 as an input. Now let's understand how the for loop works in this context. So the loop starts with S initialized to 5, and it checks if S is less than or equal to 12. If true, it executes the loop body. And inside the loop body, it sets the pin mode of that current switch pin S to input. So after completing the loop body, it increments S by 1, and it goes back to the condition check, and the loop continues until S becomes greater than 12. So in summary, this for loop is a concise way to configure a range of switch pins 5 to 12 as inputs, and eliminates the need to write multiple pin mode statements for each individual pin, and makes the code more readable and maintainable. And after the setup, there is the loop area, which initializes the hardware components. So uint8 assembled brings about a variable called assembled to store the assembled binary value. And the for loop is designed to iterate through switch pins, starting from pin 5, SS equals 5, up to pin 12, SS less than or equal to 12 inclusive. So within each iteration of the loop, digital read SS reads the state high or low of the current switch pin SS, and SS minus 5 calculates the shift amount based on the current switch pin number, and this ensures that the shift starts from 0 for the first switch pin 5 and increments by 1 for each subsequent pin. It performs a bitwise left shift on the result of digital read SS, effectively assigning different weights to the switch states based on their pin numbers. An assembled OR performs a bitwise OR operation between the existing value of assembled and the result of the left shift, and this combines the information from different switch pins into the assembled variable, where each bit represents the state of a specific switch pin. For example, if SS was pin 6 and it was low, digital read 6 will return 0 for the SS minus 5 part. Because SS equals 6, the shift amount is 1, 6 minus 5, and the result of the left shift operation is 0, since 0 bit shifted left 1 is 0, and since the left shift result is 0, the value of the assembled remains unchanged for this switch pin unless it was at a 1 before. And now let's say the switch connected to pin 6 was high. Digital read 6 will return 1 for SS equals 6. The shift amount is 1 because 6 minus 5, and the result of the left shift operation is 2, since 1 bit shifted left 1 is 2 in binary, which is 00000000010. The existing value of assembled is combined with the result of the left shift using the bitwise OR operation. For example, the current value of assembled, let's say, is 00001100. After the OR operation, it becomes 00001110. Here the pin number SS is printed into the serial monitor, and then a tab, and then the binary value of that pin, so 0 or 1. Now with this new assembled value, latch pin from 595 would be low, so this new data can be transferred, and the shift out function sends the assembled binary value to the 595 shift register, MSB is just most significant bit, and assemble is the binary value that needs to be shifted out. And after it is shifted, latch is high, so the finite file can latch the data into its internal storage register, effectively transferring the data from the shift register to its storage, which will be represented into the bar graph. And serial print in ln just prints the assembled binary value to the serial monitor in binary format, allowing the user to observe the binary value that was just sent to the shift register. And finally, there's a 1 second delay between interactions of the loop to ensure that the data transfer to the shift register has been completed. Thanks for watching.